Have you ever stopped and wondered what really happens when you flip a light switch? It seems like magic, doesn't it? One moment, a room is dark, and the next with a simple click, it's flooded with light. But it isn't magic. It's science. Deep inside the walls and within that lamp, there's an invisible highway of energy at work called an electric circuit. This isn't some complex high-level concept reserved only for engineers in white lab coats. It's something all around us, powering our phones, our video games, the tiny blinking light on a smoke detector. Our goal today is simple and exciting. We're going to pull back the curtain and understand the basic, fundamental ideas behind electric circuits. We'll do it with simple words and clear examples, so you can see the science in action everywhere. Think about it for a second. That television you watch, the computer you use for homework, the refrigerator keeping your snacks cold. They all depend on the same fundamental principles. They all need a complete path for electricity to do their jobs. It's like a secret language that all our gadgets speak. By the end of our journey today, you'll not only understand this language, but you'll also be able to look at the world around you with a new sense of curiosity and understanding. You will learn the essential parts of any circuit, see how they connect, grasp the core rules that govern them. This is the first step into a larger, more electrifying world of physics and engineering. So let's get started and unravel this fascinating mystery together. An electric circuit is, at its heart, a loop. It's a continuous, unbroken path that allows energy to travel from a starting point, do some work, and then return to where it began. Imagine a race car on a circular track. The car needs to complete the full lap to finish the race. If there's a break in the track, the car stops, and the race is over. Electricity behaves in a very similar way. It needs that complete closed loop to flow. A switch is simply a tool we use to create or remove a break in that track. When you flip a switch to the on position, you are essentially lowering a drawbridge, completing the path, and letting the electrical energy race along its way to power something like a light bulb. So, the next time you turn on a lamp or power up a device, take a moment to appreciate the elegant simplicity of what's happening. You are the master of a tiny, invisible highway, commanding the flow of energy with a single touch. This essay will be your map to that highway. We are going to explore its main components, the rules of the road, the different kinds of routes it can take. To truly understand an electric circuit, let's use an analogy as common as turning on a faucet. Varpat satter, and wartstocks, water flow. Barring through pipes. Imagine a system of pipes connected in a large circle with a powerful pump. The pump provides the push, the pipes provide the path, and somewhere along the path, you might have a water wheel that spins as the water flows past it. An electric circuit works in almost the exact same way. It's a closed path designed for the flow of electrical energy. This flow isn't made of water, of course. It's made of tiny charged particles called electrons. But the concept of a closed-loop path is absolutely key. If you cut one of the pipes in our water system, the water spills out and the wheel stops turning. The same is true for electricity. If the path is broken, the flow stops. Every simple circuit, from the one in your flashlight to the ones in your tablet, is built from three essential parts. First, we have the source. This is the powerhouse, the part that provides the energy or the push for the electricity. In our water analogy, this is the pump. In a real circuit, a common source is a battery. A battery stores chemical energy and converts it into electrical energy, creating the pressure needed to get the electrons moving. The second essential part is the path. This is the route the electricity takes, the pipes of our analogy, typically wires that let electricity flow easily. Conductors like copper are designed to let current pass with little trouble, just like smooth, hollow pipes let water flow. The third and final key component is the load. This is the whole reason we build the circuit in the first place. The load uses electrical energy to do something useful. A light bulb converts electrical energy into light and heat, a motor into motion, and a speaker into sound. Without a load, the circuit would just be a loop of energy with no purpose. Put it all together, the source pushes, electricity flows along the path to the load where work is done, and then returns to the source to complete the loop. The source, the path, and the load must all be connected in an unbroken chain. So Suberdetster and C in Nixteber Dapper. Sutaktim for Dexti. Sobator Jetim. Arjur Jotim. Open or close the path on command. Now that we understand the basic structure of a circuit, let's zoom in and learn the language used to describe what's happening within it. Three of the most important words are current, voltage, and resistance. Let's start with current. Electrical current is the measure of how much electricity is flowing through a point in a circuit over time, like the rate of water flow in a river. A wide, fast-moving river has a high current, while a slow, trickling stream has a low current. In a wire, it's the number of electrons passing a point each second. We measure current in amperes, amps. Next up is voltage, the push or pressure behind the current. It's the force that makes the electrons move in the first place. In our analogy, voltage is like pump pressure. A power outlet provides a big push, high voltage, while a small battery provides a gentler push, low voltage. We measure voltage in volts. Finally, resistance. How much a material opposes or slows down current, electrical friction. A smooth, wide pipe means low resistance and easy flow. Squeeze it or fill it with gravel and the flow struggles. High resistance. Different materials have different resistance. Copper wire has very low resistance. An incandescent filament has very high resistance and glows as electrons struggle through it. We measure resistance in ohms. These three concepts, current I, voltage V, and resistance R, are connected by Ohm's law. Current equals voltage divided by resistance. Increase voltage, the flow increases if resistance stays the same. Increase resistance, the flow decreases if voltage stays the same. It's the simple math behind complex electronics. Let's move from theory to practice and build a circuit in our minds, the classic example that shows it all. All we need are three simple items: a source, a path, and a load. We'll use a 1.5-volt battery, two short copper wires, and a small flashlight bulb. First, connect one wire to the battery's positive terminal, then to the bulb's bottom tip. Right now, nothing happens. The circuit is open, a road to a dead end. Now connect the second wire to the bulb's threaded side, and touch its free end to the battery's negative terminal. The instant that connection is made, the loop is complete, and current flows from positive, through the first wire, the filament, the second wire, and back to negative. The bulb flashes to light. Success! The battery provides the push, voltage, which drives the flow, current along the path, and at the filament, resistance. Energy turns into light and heat. Break the loop anywhere, and the flow stops instantly. This simple, beautiful system is the foundation of all electronics. There are two primary ways to connect multiple loads into a single circuit: series and parallel. Series is one continuous chain, one path for current. Electricity must pass through the first bulb, then the next, and so on. A classic example is old holiday lights. One burned-out bulb broke the circuit, and the whole string went out. Voltage is shared among loads in series, so each bulb glows dimmer. In a parallel circuit, each component has its own branch. Current splits between branches and rejoins before returning to the source. This is how homes are wired. If one bulb burns out, only that branch opens. The others stay lit. Each branch gets the full source voltage, so parallel bulbs glow as brightly as a single bulb, but drawing more total current drains the source faster. Knowing series versus parallel is crucial for reliable, efficient designs. As we explore the amazing world of electric circuits, there is one topic more important than any other: safety. Small batteries like 1.5 volts or 9 volts are perfect for safe, hands-on learning. Their push is too low to drive a harmful current through your body's high resistance. But wall outlets are a different story. High voltage, like 120 or 240 volts, can be extremely dangerous. Never play with outlets, cords, or plugged-in appliances. Report damaged cords, and leave household wiring to trained electricians. Experimenting with a battery is like a garden hose. Wall power is a fire hydrant. We learned that an electric circuit is a closed loop that allows electricity to flow. Every circuit needs a source to provide the push, a path for electricity to travel, and a load to use the energy. We demystified the key terms. Current is the flow, voltage is the push, and resistance opposes the flow. We saw these ideas in a simple battery and bulb circuit, and explored series, one path, and parallel, many paths. The biggest takeaway: electricity needs a complete path to do its work. Stay curious, visualize the source, the path, the load. In every blinking light and spinning motor. The world is full of fascinating circuits, just waiting for you to discover them.